I'm Vivian Robinson, a PhD physicist with over 50 years of postdoctoral experience. I was brought up in rural Australia, in one of the more remote parts of the Western world, where you had to learn to improvise to get by because things were not easily obtained. So along the way, I learned to improvise a little bit and do things my own way. From an early age, I always had a fascination in what the hell's going on in the world or the universe. So the only way I could work that out was to study physics. And so that's what I did, going all the way through in Western Australia, graduating from the University of Western Australia, a PhD in 1970. I then worked for a government department for a while, a university for a few years. I came up with some ideas that I thought were pretty good, but that's not what the rest of the world thought. So I had a lot of rejection letters, let us say. Undeterred, I decided to just continuing my day job at the university. I would use the university's facilities to demonstrate experimentally that, hey, I was right. And come mid-1970s, I was starting to get much more advanced than anybody else. I then developed some equipment and some products which I took to the commercial world, and which of course is the world of reality. That taught me, first of all, if you've got a new idea, don't bother trying to publish it. The referees will only reject it, and you spend most of your time trying to overcome their objections rather than getting on with it. So ultimately, when I did introduce my it was a backscattered electron detector for use in scanning electron microscopes, it totally revolutionized the way that electron microscopes were used. And that was in a backdrop, of course, of all the world's experts saying it would never work. So if you think that I have any respect for world experts on anything, forget it, unless it makes sense, common sense. And I'm afraid, as you'll find out later, a lot of it doesn't. At the same time, I came up with a way of looking at, in an electron microscope, you have to have it in a vacuum and it must be conducting, otherwise you just can't view it. And I came up with a way where you could look at uncoated or non-conducting liquid specimens in the vacuum of electron microscope and get good resolution. That in itself resulted, despite much criticism of it early on, that in itself resulted in about 20% increase in the worldwide sales of scanning electron microscopes. So it was a significant contribution, along with my detector, which at one stage in the late 1990s, I was the most popular brand name accessory on all scanning electron microscopes throughout the world, which I thought was quite an achievement. It was at that stage, well, before that achieved, I was working at the university and licensed a company to make them. After a while, I decided I could do better off out in industry and join the real world, which an academic joining the real world is not easy because you're used to it, the way academics think and do things. The real world is entirely different. It's probably best summed up by, in academia, you sit for exams, and if you get 90% for 6 exams and 10% for 7th, you finish up with an average of about nearly 80%, which most academics would consider pretty good. In the real world, you're only as good as the thing you do worst. So if you do 8 things good and get 100%, and you do 1 at 10%, your result is 10%, unless you can pay somebody to do what you're no good at. That's another lesson that also taught me, is that most academics think the important parts of a conference are the papers that are given there. No, that's not true. The important part of a conference is the equipment that is presented there, because when you're presenting a paper at a conference, all you're doing is showing people what you have done. When you stand on an exhibition floor at a conference, you're giving people the opportunity, everybody the opportunity to purchase your equipment or use your equipment. And and that way, instead of being just something that's useful for 1, 2, 3, 5 people, it's something that's useful for thousands of people. And a lot of people, of course, take pride in how they received 100 reprint requests for a paper back in the old days. And yeah, well, give me 5,500 requests for detectors. It's and of course all the electron microscope companies taking, and that's worth vastly more than any academic achievement, but it's a quiet achievement. That working in industry instead of university gave me the opportunity to study what I wanted to do. So my interest always in is what the hell's, what's the universe made of and how does it function? So listen to academics and you think, this is Taurus excreta or whatever other polite, but you can't talk to them about it. They think it's wonderful and waffle on in mathematics. So I just worked away and started developing an idea. This is way over 30 years ago, and that idea was that the first part of it was that electrons were actually photons making 2 revolutions within their wavelength. I tried a bit of publishing, and all I got from, well, yeah, but what's it revolving around? Okay. So I just went ahead, and much to my surprise, well over a decade later, I thought, nearly 15 years later, I was finding, other people are actually working on the idea as well. The thing is that by this stage, by not having spent a lot of time to get it published, I then extended the work so that it wasn't only electrons, but it was protons and neutrons and neutrinos and photons, and then expanding them into nuclear physics, structure of subatomic particles, and all that sort of thing. Okay, was it in great detail? No, but it all seemed to match up. And then having a few grey hairs and being able to spend a bit more time doing what I wanted to, I started to polish it up a little bit more. And until you've got what you call a picture of the universe, which I described in a book I've authored but not attempted to distribute, is called How to Build the Universe, where I start out from the smallest subatomic particles and you go all the way through to the large-scale structure of the universe, and you suddenly find that topics that people think are horrendously complex, like Einstein's theories of relativity, all the problems in nuclear physics, the difficulties they're having subatomic particle physics and dark matter and dark energy and that. You think, no. It's time to start all over again. So that was my background. I'd just like to tell you a couple of things about my philosophy in this study. The first one is that the universe and everything exists, everything in it exists in three spatial dimensions with time flowing through them. Now, they've been using particle accelerators for decades trying to find something else. They haven't found it. So, hey, I think experimentalists are pretty good. I was one myself, and I'm quite prepared if experimentalists have found something or haven't found something after a long time, I'm quite prepared to admit it does or it doesn't exist. The other thing about the universe, it has existed and self-functioned for many billions of years. So it must be simple and inherently stable. So this idea, it's fine, everything is finely, we live in a universe where everything is finely tuned, and there are 10 to the 60 other universes out there that might be imbalanced. Forget it. This universe, to stay stable for so long, just has to be inherently stable. Now, if something doesn't go wrong in billions of years, my impression is it's quite stable. See how long you can drive your car without something going wrong. You won't get a billion years out of it, that's for sure. So getting back, experimenters have done, I think, a really good job in documenting things. In many cases, they've actually been directed by theoreticians to look for something, and they found something entirely different. So I'm therefore prepared to think that their results were unbiased. So, look, the gaps we have in our knowledge, I think, are due to theoretical deficiencies, not to any experimental, not the experimentalists haven't been looking hard enough. Perhaps the best example I can give of this is nuclear physics. It was about 1915 when it was first postulated that the atoms were made up with a central core of a nucleus and electrons going around it. It was the 1930s that Weizsäcker first came up with a model of the nucleus. And that was nearly 90 years ago. And guess what? They still haven't got a good model of a nucleus that can describe its properties and be used for making useful calculations across all 200 or whatever it is nuclei that there are. That's not because the experimentalists haven't been trying hard enough. It's the theoreticians have just got the wrong theory. At least that's my opinion. Now, things happen for a physical reason. And when you want to work out what's going on, or at least my philosophy of working out what's going on is to first of all work out what was possibly the physical reason. Then having an idea of what the physical reason is, you use mathematics to calculate the magnitude of the physical effect. And if the mathematical calculations match observation, hey, it's worth continuing. If you don't just rewrite the mathematics. You've got to turn around and come up with some other idea. Now, I know a lot of physicists disagree with that because they all look at Einstein's work, who was brilliant making these predictions from an entirely mathematical point of view. Yes, he was. And I think most physicists have tried to emulate his work by using mathematics. In my particular case, I tried to work out what the physics was, and then see if I could apply that physics. Did I get his calculations? And the answer in both special and general relativity theories are yes in both cases. And in both cases, by taking that approach, I'm able to extend them. So, if you want to think that your mathematics is great and mathematics makes things happen, don't talk to me. I might have a few words. Well, that's not necessarily true. There is one chance, I will admit, where mathematics makes things happen. If somebody hacks into your bank account and uses a few numbers and rearranges them, that is when mathematics makes things happen, and probably to your disadvantage too. But if you're coming up with a model about something, a new model for an electron or a model of the way things happen, well, particularly for particles, don't just think of it in terms of, yes, I have this new model for an electron. Think of it in terms of how does this model interact with the rest of the universe. And I know how it acts with the rest of the university. And I think the university guys think it's really great, but the real world, universe at large, no. So when you're doing something, don't just try not to limit to just one field of influence, one area. Just think a little bit more widely about it. Another one, I notice everybody has a big push for this grand unified field theory of everything. In reality, it is particles that generate fields. I know all the theoreticians are out there and saying that particles are just oscillations in some field or something like that, and they introduce complex tensor fields and Higgs fields and all sorts of things like that. But unless there's a particle to generate it, it isn't there. At least that's the philosophy I use. Another one I use is the most common property of the universe is empty space. And if you don't believe it, have a look at a few pictures of telescopes, and then have a look at them. Look what they know about the atom. You've got this tiny, dense little bit, about 10 to the minus 15, or 2 or 3 times 10 to the minus 15 meters in diameter, and then you've got these very, very small things called electrons going around and extending that dimension to about 10 to the minus 9 centimeters thereabouts. And most of that is just empty space. So, if you're going to build a universe, at least show how empty space can support it. Another idea I had was that I love the old school guy. I love classical mechanics, classical physics, which is basically Newtonian mechanics and Maxwell's equations. Now, they actually govern the behavior, but for most of the things that you use, they govern behavior in the real world. Sure, GPS system needs a little bit of fine-tuning by relativity, no problems. And yes, the transistor operates on quantum properties, so they say, but I won't go into it now. But my impression is that both the general and special relativity theories depend upon photons. And when it comes to quantum mechanics, Newtonian mechanics and Maxwell's equations work very well when things are a continuum, which is mostly what they are around you. It's only when you get down to dimensions that are so small that they are the ones that generate, like an electron is the one that generates an electric, it's usually the one that generates an electric field. When you get down to the size of an electron, you run into problems with Maxwell's equations. However, when you've got enough electrons together so that you're forming a continuum, at that stage, Maxwell's equations work fine. But if you know the structure of an electron, you'll then find that you can use Maxwellian and Newtonian concepts to work out a whole lot of things. And I'm going to include in that a whole lot of quantum mechanics. They're all very, very simple things. And forget about what the guy who says, if you think you know, or when you think you know what you do, what's going on in quantum mechanics, you're wrong. I'd argue with him any day. I'm quite sure I'd come out on top. Newtonian mechanics also breaks down at very high gravitational fields and at very high velocities. But again, just knowing the properties of photons is all you need to use Newtonian concepts to get the answers in both of them. Now, I'll point those out later for those who stick around long enough and listen to the rest of my talk. Another one is human observations. A lot of people have this philosophical idea that somehow human observations interfere with the world or the universe. Well, I can tell you now, there's no way the rest of what's happening in the Andromeda Nebula has anything to do with the way humans look at it 2 million years later. I will acknowledge that during that human observations as a result of an experiment can affect the result, but that's as far as I will go. And probably a final point in my philosophy, and the first part of this is due to John Williamson, who came up with these equations, which basically says that the sum of all changes equals 0. And these are just the normal conservation laws, and he's found a way of applying them. And I'd apply another one as well, which I'll explain, you'll know. Each individual change is governed by an equation which just says the change of energy, or delta E, tends to 0. You'd more know it as the principle of least action, or as quantum physicists like to do just to confuse everybody, the principle of stationary action. I'm thinking, stationary action, yes, that's about up to par for theoretical physicists. So that's just a summary of me and my philosophy. And if you hang around long enough, you can see some of the results that it produces, and I hope you'll be pleased with them. Thank you.